This is Pre-Calc section 5.1, inverse functions. Most of this should be review from college algebra. There are a few things at the end that will be new for you. A function f is called one-to-one if, for elements a and b in the domain of f, a not equal to b implies f of a not equal to f of b. And what that means is, say we've got a bunch of ordered pairs. Let's say 1, 4, 2, 6, 3, 8. If a is not equal to b, meaning if the x values are not equal to each other, then the y values cannot be equal to each other either. So take a look at some of these graphs and see if this fits. Take a look at these ordered pairs. This is the ordered pair 0, 1. This might be 1/4, 1 1/4, 1/2, 2, etc. At no time did I repeat the y value. Therefore, this function is one-to-one. And one way we know that the function is one-to-one without looking at the ordered pairs is that the one-to-one function must pass the horizontal line test, which says any horizontal line you draw can only cross the graph once. And that is the case with this. So this function is one-to-one. Let's draw some horizontal lines here, like right there. That horizontal line is intersecting our graph twice. That says this is not one-to-one. And how does that apply back to the definition? It's this. Take a look at this ordered pair. This ordered pair, this will be easier to see. This ordered pair is -1, 1. This one over here is +1, 1. Here we have a not equal to b, but f of a does equal f of b, and that's what makes this not one-to-one. Take a look at this graph, 6 over x minus 5. Does it pass the horizontal line test? Yes. Every horizontal line I would draw only intersects my graph once. So this is one-to-one. Here I've just got a bunch of ordered pairs that I went ahead and put on the graph to reiterate what I said on the other screen. We know that this does not pass the horizontal line test. Take this horizontal line right across here. It's intersecting my graph here and here. That all by itself tells me that it is not one-to-one. And the reason it is not one-to-one goes back to the definition. Here we have a not equal to b, but f of a and f of b are the same. In other words, the y values are not allowed to repeat. Now we also looked at this graph in college algebra. To find the inverse of a graph, just switch the x and y coordinates. So what I have here in red is an initial graph of f of x, which happens to be x cubed plus 2. In blue is g of x, which happens to be the cube root of x minus 2. And we have this line in the middle. This green line is the line y equals x. If you take each of these red dots that I've highlighted, there they are in the chart, and we just reverse them, -1, 1 becomes 1, -1. 0, 2 becomes 2, 0. 1, 3 becomes 3, 1. And when I talk about reversing them, that is the x becomes the y, and the y becomes the x. So take a look at where those are. Over 1, which is about right there, down -1. Over 2, 0. Over 3, up 1. And those are giving us the points that are on the blue line. So very easy to find the inverse of a graph. You just have to switch the x and y coordinates. The other thing that's important about this graph for you is that when you do the inverse of a function, it is the reflection across the line y equals x. If you could lay a mirror down right along this green line, you would see the reflection of the red is exactly lined up with the green. So take this graph that's already graphed for you. There's the ordered pairs. Let's swap them around. We're going to get 0, -4. 0, 4 becomes 4, 0 when I make the switch. And -2, 2 becomes 2, -2. So 0, -4 is down here. 1, 2, 3, 4. I have to estimate a little bit. 4, 0 is about right here. And over 2 down 2 is right there. If I put the line in there, there's the line. And this right here is my line y equals x. So you can also see that the original line reflected over this line here, which is the line y equals x, does give us this line right there. Can you find the inverse of a set of points? Yes, very easily. You just take those points and you swap them around. So instead of looking at a graph and having to pick out the original points yourself, you just swap them around from the ordered pairs. So that's even easier than looking at a graph. So to find the inverse of a set of points or a graph, all you have to do is swap your x and your y, and that will be your new function. Now, the steps to find the inverse of a function when you're dealing with an equation like these. Number one, you replace f of x with y. So instead of f of x right here, I'm just going to put y. You switch your x and your y. Remember, to find the inverse, we switch the x and the y. So x comes over here, y will come over here. And then we rewrite this equation right here so that the y stands alone. So subtract 5 from both sides, divide both sides by 2, and this is our inverse. Now, it says if f does have an inverse function, replace the y with this notation right here. You've seen this notation before. This is the inverse notation. So my answer would be inverse of the function equals x minus 5 over 2. Now, it's okay if you want. You could separate this out to be x over 2 minus 5 halves, but you don't have to go that far. Now, go back a second. When we solve for y, if you pick up a plus or minus in the solving, then the inverse does not exist. And the reason is this. X squared plus 2, I'll do it algebraically in a second, but x squared plus 2 is a parabola that's up here a little bit. It does not pass the horizontal line test. So this function has no inverse. And as far as the algebra of it, here's my steps. Put my y instead of f of x, swap my x and the y. So now it's x equals y squared plus 2. Subtract 2 from both sides. And to undo this y squared, take the square root. And you should remember that as soon as you take the square root of both sides when you are solving, you get a plus or minus. So algebraically, the plus or minus tells me there is no inverse. Graphically, the fact that it doesn't pass the horizontal line test tells me that there is no inverse. Now, this is the newer stuff. We did not do this in college algebra. Find the inverse of a rational function. It is still the same steps we did on the other page, but they get just a little bit more complicated. So I'm going to put y in place of f of x. Then I'm going to swap out my x and my y. X comes over here, and y needs to be written both places. Y for that, and y for that. So it is still a rational function. But I need to solve this for y, and the only way to solve this for y will be to give this a denominator of 1 and cross multiply. When I cross multiply there, distribute, I get xy minus x equals 2y. So that's not too bad. The next thing is, if I'm going to solve this for y, I need all of the y items together on the same side. So I'm going to send 2y over here to this side. And you know when you change sides, you need to change the signs. So when I move the 2y over, it becomes negative 2y. I'm going to send the negative x over to the right side, and it becomes positive x. Y is on the left side. It is written twice. I need to have it written once, and the only way to make that happen is to factor out a y, which is a good thing because this is y times this binomial. To get that y alone, I need to divide both sides by x minus 2. So that gets rid of the x minus 2. The y is standing alone, and now I have x over x minus 2. And my inverse notation says x over x minus 2. The next thing we're asked for is to name the domain and range and sketch a graph of f, meaning the original function. I'm going to graph the original function first because I think that's easier to name the domain and the range from the graph. The original function is right here. We're going to use our graphing calculator in a second, but we can do the asymptotes very easily. We know there is a vertical asymptote at 1, which is about right here. There's a horizontal asymptote at y equals 2 because of the ratio of these coefficients. So up here at 2 is my horizontal asymptote. And go ahead and enter that in your calculator, and you can see that the curve looks like this. Now, one comment, if you're going to enter this in the calculator to look at the graph, be sure you enter parentheses around that x minus 1. Now that I have the graph drawn, I can talk about domain and range. The domain of the original function is equal to the range of the inverse. Think about it. You have swapped x and y, so when you swapped x and y, you also swapped the domain and the range. So as soon as you name the domain of the original, you automatically already know the range of the inverse. So the domain of the original will come in from negative infinity. It will go all the way up to the vertical asymptote, which is at 1, and then it'll pick up again on the other side of the vertical asymptote. By the same token, the range of the original function is equal to the domain of your inverse. So your range of the original function is negative infinity up to that horizontal asymptote at 2, union with 2 up to infinity. All right, this problem is asking me to apply the inverse function to 5. Well, I don't have the inverse function. What I would like to do is to take these original points and find the inverse of those points. So this point right here, let's say, is 0, negative 3. This point over here is 6, 0. This over here is 8, 5. Those were some points that were on my original function. If I want to find the inverse of those, I just swap them around. Negative 3, 0, 0, 6, 5, 8. Well, the only one that is important to me is this one right here, because it says find the function value in the inverse function of 5. Well, I just found it, 5, 8.